this loud enough? Yeah. Okay, welcome to the last lecture of INF 3331 and INF 4331. So this is really let me just switch the microphone. Okay, so I hope you're all doing your last assignments and due next week, if I'm not mistaken. And then we have one more week peer review. And that peer review will be also based on a pull request, just like last time. I'm contemplating probably what will happen is that you will make a pull request, but I also want you to accept the pull request that you receive for your own repository. So there should be kind of, maybe you receive the pull request and then you review the changes that have been proposed, and you either decide that you accept them, but if you're not happy with the changes, you might also reject them and argue why you don't want to have these changes in your pull request. Right? Because that's actually what happens in real development. You make proposed changes and they might be rejected because maybe you're not following the standards of that pull repository.
What if there's something that is okay and you want to accept it, but there's other things you don't want to accept?
Right.
This pull request is that either you accept all of it or none of it, right?
It's a good question. So the question is, what happens if you want to contribute something to a software project and you make a big pull request, and then the reviewer says, well, parts of it is okay, but parts of it is not so good. So generally my advice is to make, good advice is to make smaller pull requests instead. So kind of try to make the smallest possible improvements and propose them, and then rather have multiple pull requests for these different things. And some of them will then be accepted and others will be rejected. So often it's better to kind of smaller changes in general. Also when you do commits, for instance, it's much better to commit smaller things more often rather than waiting for a long time and then commit the entire assignment, for instance, in one commit. But I mean, in the context of this assignment, we will just make one pull request where you propose your changes, and then that's good. Okay, but the big topic for our last lecture is machine learning. And so, of course, this is kind of a hot topic, and I hope it's going to be interesting for you. I will give you a very brief introduction to machine learning. But with the power of Python and what we've learned as part of this lecture, we will see that we can actually, in 1.5 hours, we will be able to kind of program quite powerful machine learning algorithms. And okay, so what this lecture will cover is essentially, I will give you a very high-level introduction to machine learning, and I will present to you a package in Python that you can use through machine learning, and that package is called Scikit-learn. But before we start, we should probably talk about what machine learning actually is. There's many different definitions. The one that I've chosen is written here. Machine learning is the semi-automated extraction of knowledge from data. Okay, so if we break this sentence down, the first part that we should look at is these last three words, knowledge from data. So we're trying to extract some information from lots of data that we've acquired before. And so typically what we start with is that we have a question that we want to have answered, and we have lots of data, and then we use machine learning to extract the answers from that data. The second part is this automated extraction. So we don't want to sit down and manually dig through their data to find the answers to our questions, but instead we want to use algorithms to find them for us. And then finally, there's this word semi-automated here, indicating that maybe it's not quite as automatic as we would like to, but there's still kind of human expertise involved. And now if you look at different machine learning algorithms, you can broadly categorize them into two categories. So it's either we're talking about supervised or unsupervised learning. So when we come to supervised learning, the core idea is that we want to make predictions from data where we have previously acquired a data set where we know the answers. So we have a data set where we have the inputs and the known outputs, and then we do a training process, and then afterwards we can make predictions. So a typical problem setup is classification. The idea of classification is that you get in a new object and then you want to classify it into different parts. So for instance, you might get an apple and a pear, and your machine should decide if something is an apple and a pear. And so a typical example of that, you use that every day, and that's spam recognition. You get a new email in, and then in actual machine learning, typically support vector machine specifically decides if that mail should be moved into the spam folder or not. Another example is regression. So regression is essentially the same as classification, just that instead of classifying into a finite set of boxes, we now have an infinite number of values that we want to predict. So an example, for instance, is if you want to predict the life expectancy of a person. Right? So you know some properties of the person, maybe when he was born or she, and if he smokes, and you know if he does sport. So then from this data you want to predict what the age is. And the age is kind of a continuous value, right? It's not just a fixed number of outputs. So this is regression. And so regression is used a lot in practice. So if you look into finance, for instance, right, so of course they have lots of data points of the past, and they want to predict how is that going to how's the behavior in the future, for instance. Also, if you look at weather modeling, for instance, where you want to do predictions into the future. And then there's unsupervised learning. And essentially, unsupervised learning is it's the problem where you want to learn from data without having any output knowledge. So one idea is kind of clusters. So imagine you've collected loads of different samples of flowers, but you don't have an understanding on how they connect to each other, and you just want to cluster them in a way. And so this is what, for instance, an unsupervised learning problem would be. And of course, there's many different answers. So here you would cluster kind of these dots into green, blue, and red ones. But maybe that's just one way of clustering them. There might also be another one. So in this lecture, I will only mostly focus on supervised learning. So to get your feeling a bit better for what is supervised, so there's a kind of a very fundamental problem. And so if you have a specific questions that you want to have answered, the first thing that you need to understand is, am I facing a supervised learning problem or an unsupervised learning problem? Because depending on that, you will have to use completely different approaches. So let's look at some problems and let's decide if they are supervised or unsupervised learning problems. First one is, given a photograph of a person, identify the person in the photo. Do you think that's supervised or unsupervised?
It's supervised because you have the information about the various people already in a database, and then you check against that database to identify the person.
Very good. Right, so this is a classical example of a classification problem. We have some pictures of people, and then we get a new picture, and then we just want to classify that new face into the existing classes. So the next problem is actually one that in 2009 was worth $1 million, and it's called the Netflix prize. And Netflix is very well known nowadays. So they asked the question, given a list of movies of a person has watched and their personal rating of the movie, recommend a list of movies they would like. So, of course, a very relevant question for Netflix. Do you think that's a supervised or an unsupervised problem? Anyone else still in here this? No? Yeah?
Well, isn't it between both to in a way use supervised and unsupervised, because we don't really know what the movies, you don't have a fixed list of, you have all the movies you can check that would be definite which ones you watch.
Right, so maybe something in between. What do you think?
I would say it is supervised because you have the list of his personal ratings. So basically, if a movie is similar, fit the same description as one he likes, then he probably will like that movie too.
Mm-hmm. Yeah. So I would also say it's probably more supervised problem, because you have you know what people, you kind of have a data set with the output, because you can check what people are watching into the future, right? So they kind of, people watch something in the past and then they watch something in the future. So you have a training set where you have the people and you know what they like to watch. And so then once you get a new person in, you can try and find similarities and try to predict what they might not watch. Okay, so the last one, given a mixture of two sound sources, for example, the person talking over some music, separate the two. So this is a problem, for instance, if you talk on the phone, right, in the discotheque, in the disco, and you want to, of course, the other person doesn't want to hear the background noise; it just wants to hear the voice. So, any ideas what this would be? Yeah.
Well, both. The initial part of separating the two sound sources is the clustering task, so that would be unsupervised. But you would also have to know which switch, which would then have to be labeled either manually or through some such inputs.
Yeah. So I guess it really depends. If you already know that your sound sources consist of one person talking and something else, then it's probably a supervised learning problem, because you can.
If it is a known music and you have a separate tape or source with only the music without the sound, then you can easily extract spoken conversation on top of it.
But if you don't know anything about the sound sources and you just know
Then
it's
it is
kind of,
unsupervised.
then it would be an unsupervised one. So in this lecture, I primarily want to talk about supervised learning, and that's part of the reasons because it's kind of the most common questions that we ask are solved by supervised learning algorithms. And so if we want to apply supervised learning, we have to do two main steps. The first one is called model training, and the second one is predictions of new data. So in the model training step, what we're doing is we're using labeled data. So that's data where we have the inputs and we know what the answers are. And we use this data to learn the relationship between the data, between the inputs and the outputs. So this is visualized here, and it's the blue arrows. So the inputs, for instance, could be documents, it could be images, it could be an email, right? It could be the text of an email. And then the labels, this is the known outputs. So this could be, in the case of spam, it could be just a yes or no, indicating if this particular email is a spam or not. Maybe you're trying to identify faces and images, then it would be, then the input would be the image and the label would be the name of the person, for instance. And so then what we do is, well, we take this input data and we extract so-called feature vectors. I'll explain later what that is. But then essentially this is the where the magic happens. We feed that all into a machine learning algorithm, and that machine then learns based on that data. And the second step is the prediction step. And the prediction step, here the main idea is that we get in a new data point, and where we don't know what the label is, we don't know what the outcome is. And we want to use our machine learning now to predict the most likely output. So that would be, for instance, a new email or a new face. Again, we would extract relevant features, and then we would use this trained machine and use it as a predictive model to predict what the expected outcome would be. So this label would be, again, the name of the person, or it would be telling us if an email is a spam. So conceptually, when we work with this setup, right, there's some important design decisions that we need to make. So first of all, we need to figure out what are these feature vectors, that kind of describe our input data in the most relevant way. This is something that every machine learning expert needs to think about. Then, of course, what is very important is there's many different machine learning algorithms, and we need to decide which one is most suitable for our algorithm. And then finally, once this entire machinery has been set up, we need good metrics to evaluate the quality of our predictions that we make. And all of these three will talk now. I will present now. So the package that we will use for machine learning is called Scikit-learn. And it's a Python module that implements many different commonly used machine learning algorithms that are out there. There's many other machine learning. Nowadays, there's many other options that you have. There's, for instance, Google. Essentially, all the big tech companies develop their own machine learning toolkit. Google develops their own. There's Facebook has their own, and so on and so forth. So TensorFlow and Torch, for instance, are big others. The reason why I present Scikit-learn is because it's very kind of user-friendly, because we can use many different algorithms using the same interface. So later on I will show you that we try out many different algorithms with just essentially changing one line. And it's got sensible default settings, meaning that we can essentially just try it out without having to understand in detail the different algorithms. And this has got quite good documentation. So if you go to the website here, Scikit-learn, you see they have really nice demos for various different types of problems. And they're built on NumPy and SciPy, meaning that a lot of the data structures that I've taught already in this course is going to be familiar to us when we now use it. So disadvantages are that Scikit-learn is it implements mostly established machine learning algorithms. So if you really want to be kind of cutting edge, then you might have to switch to another library. And also, it's not really optimized for very large data sets. So if you're really looking in kind of deep learning, for instance, and you want to run your training problem on GPUs, right, then you have to switch to a different platform. But we will learn a lot of the, as I mentioned already, so we will use Scikit-learn, we will use NumPy and Matplotlib, and so pandas is also something that is often used for data preparation. Okay, installing Scikit-learn is fairly straightforward. You should all be familiar with that. If you have Conda, do Conda install Scikit-learn, and otherwise pip3 install Scikit-learn. And that was it. And then we can import it. So just import sklearn. And here's a trick that I use very often that not only works for Scikit-learn, but essentially for any library. If you want to check the version that you have installed in the system, you can just type in Scikit-learn or the module name __version and you'll see if it's a well implemented library, then you should see the version number that you're working with. There's also another really useful thing that I often use is __file__. And that actually gives you the path where that library is installed. So this is just a side comment. Sometimes that's useful to know. If you have multiple installations of the same library and you're confused on which one you're using right now. Okay, and we will also use matplotlib, so I just import this now. So the most important thing that you need to learn to get started is how you need to pass the data to Scikit-learn for the training process, but later on also for the evaluation process. You need to understand which representation of the data Scikit expects. So Scikit expects a two-dimensional, this is now for the training process, it expects a two-dimensional array, or another word, a matrix. And that array should be a NumPy array, which we luckily know already. And so the size, okay, how big is that array? The size is it has n number of samples rows and number of samples columns. That's going to be the number of features columns. So that's the size of our matrix. Okay, number of samples, these are the number of rows. So for each row represents one sample. One sample means a data set where we know the outcome. So that could be, for instance, the email, or it could be a photograph, and so on. So sample could be a document, could be picture, sound, a video, and so on, so depending on what you're working with. And then we have the columns, and the columns represent specific features of that sample. So maybe the first column represents the first character in the email, and the second column could represent the second character in the email, and so on and so forth. If you're talking about an image, right? Maybe the first column would represent how many red pixels are in this image, and the second would represent something else. So this is something that you need to come up with, which features you want to store for your data set. The important part is that the number of features need to be fixed. So we can't have different numbers of features for the different samples. We need to decide on, we have 10 features or 100 features, and then you need to compute these features for all the different samples. Of course, in practice, we can use very high dimensional features, so we might use millions of different features, and have most of them set to 0 if you want to. Okay, so with that, we can start applying our knowledge to a first machine learning task. And that task is to make a classification of a specific flower, the iris or iris flower. And so that's a very famous machine learning classification problem because it's relatively easy. And so the iris flower has exactly comes in 3 different types, which are visualized here. So it either looks like this, or it looks like this, or it looks like this. And our task is now to learn how to differentiate these 3 different classes. And so the idea is once we get a new flower in, we can use our machine to tell us in which class this flower belongs to. So the 3 different names are Iris setosa, this one here, Iris versicolor, which is this one, and then Iris virginica, which is this one. Okay, so the goal, of course, is to predict the species of an iris flower using some measurements that we will take. And this is a supervised machine learning task. So the first thing that we need to do is we need to ask the question, what should our feature set look like? So which measurements should we take in order to do the training on our machine learning algorithm? And remember that the form of this training set needs to be number of samples times numbers of features. So, question to you, what do you think the number of samples refer to, and what might the number of features refer to in the iris example? Yeah.
The samples is the amount of measurements by other individuals of the different species that you have.
So, do you say 3? No. Number of samples?
No. Number of samples is how many you have
Right.
of the
Okay.
different sightings
Yeah.
that you have.
So essentially, we now go out into the forest and collect 100 of different flowers,
So
and
each-
then we
each
have
sample is
100 samples.
Yes.
Yeah. And so what could be, which features might we want to use for our data point? Yeah?
Characteristics of each flower and how they differ. So like,
Okay.
don't expect exactly know what differs a flower from another. But
Especially characteristics that are different for the 3 variants.
Yeah? Yeah.
I don't know if it's the picture, but the color looks different in the first two. I think that's just the.
So definitely, maybe, I mean, so color could be one, right? We could try and now look at every sample flower that we have and try to, maybe we can measure the color in some way, right? And that could be one feature. Any other ideas?
The relative size of some of the leaves.
Right?
For example, on that first one, the 3 leaves on the top is relatively small, whereas on the other ones they are larger.
Right, so we could measure kind of maybe how big these leaves are. That would be one. We could count the number of leaves, right, for the different
Yeah.
flowers, and so on and so forth. Yeah.
You feel so how far the yellow part of the bottom.
Right?
Yeah.
Exactly. You could measure kind of how long is this yellow part here, and so on and so forth.
So you would want it to be something which has predictability.
Yeah. Of course, you would. Okay, as a trained machine learning expert, you would automatically maybe have an idea on which features are worth keeping, right? So of course, we want features that distinguish these 3 classes. Of course, if all these 3 flowers have always 3 leaves, then there's no point in measuring these because it's always going to be 3 anyway, and we won't be able to distinguish them.
We can determine that for
But
looking at-
the ratio between the yellow part and the blue or bluish purple part
Yeah.
could be one feature.
Yeah, absolutely. So you can come up with many, many different ways here. So the features that I will use now is going to be the size of the leaves. And so in particular, we will measure that there's kind of 2 main leaves here on this iris flowers, is the ones that hang down and the ones that are kind of hanging upwards. And we're measuring the downwards are called sepal and the upwards are called pedal. And so we measure the length and the width of each of these. Okay, so we will have 4 features, and we will make these measurements for every single sample that we've collected. And so luckily, we don't have to go out and collect all this data. Someone has done it for us. And that's actually part of a standard data set that Scikit-learn comes with. So if you import Scikit-learn datasets, you can access different data sets that are available. And so in particular, there's this load iris function that provides us with the iris dataset. And so what we will get is exactly what we just talked about. So the data consists of the following features. We have the hanging leaf length, we have the hanging leaf width, the standing leaf length, and the standing leaf width. And then the labels, right, of course, for the training process, you also need to know the answers for all of these different samples that we've collected. And so essentially the classified answers are either Iris setosa, Iris versicolor, or Iris virginica. The three different flower classes that we want to distinguish. So Iris is now this object that this data object that I loaded in. We can have a look at it, what it looks like. You can see it's a long two-dimensional array, just like we expected, matrix. And each row here represents one specific flower that in each column represents that measurement of the flower. So this 5.1 tells us the first flower that we've collected had a hanging sepal length of 5.1 centimeters. Right? The first flower had a hanging leaf width of 3.5 centimeters, a petal length of 1.4, and a petal width of 0.2. And so we've taken these measurements for all the different samples that we have. It's a long two-dimensional array. So you can kind of check how big it is. Just apply this shape, check the shape attribute, and we see we have 150 samples with 4 features. Yeah, 4 features each. The data set also comes with this list feature names, which which maps kind of the column index to the actual feature that we're working with, which is just what we've talked about before. More interesting now is the target values, and these are now the answers for all of these different samples. And you can see in this case the samples have been ordered, so the first, 40 or whatever samples were of class 1. The next 40 or maybe 30 flowers were of class 2, and then the last ones were of class 3. And so here we simply represented them as numbers 0, 1, and 2. But if you want to get the actual names, you can use this target names list to figure that out. So class 0 represents setosa, class 1 represents versicolor, and class 2 represents virginica. So to summarize, for our training, we will use the iris.data matrix, which consists of 150 samples with 4 features each. And we will use the iris target array as the labels. So this is 150, it's an array with 150 numbers, either 1, 2, and 0, 1, and 2, depending on which class we have. So of course, this is a very high, so even before we start applying our machine learning algorithm, it's often a very good idea to look at the data in advance, to get a feeling on which information this data might contain. And so the problem often is that we have a very high dimensional data set. And so here we have 150 samples and we have 4 features. So in a sense we are in 4 dimensions. We have 150 points in a 4-dimensional space. And so of course that is difficult to plot, but what we can do is we can just pick 2 dimensions of these and plot them. And so I've written up a little script here that does that. I think it's more insightful to just look at the results. So what I've done here is now I've picked 2 dimensions, the second one and the fourth one, so that would represent the second feature and the fourth feature, which is the width of the two leaves. So here on the y-axis we have the petal width, and on the x-axis we have the sepal width. And then for each sample, I draw the point where the petal width, where it hits the petal width and this sepal width, and I color that point depending on which class it represents. Okay? And so now essentially, yeah.
I'm just wondering what the lambda I means. I know that lambda is
Yes.
a special Python thing, but I've never understood what it is.
Very good. Do you mind if I take this after the break? I can introduce lambda. Very good question. Okay, so what we can see here, it gives us an idea, right, on if we have any chance of separating these different classes. So for instance here we can see that the Setosa flower seems to have always fairly, they're all clustered down here, right? All the blue dots are clustered down here. And what that tells us is that the Setosa flower seems to have all relatively small petal widths. They're all below 1.0 essentially. While the versicolor and the Virginica flowers have petal widths that are all larger than 1 centimeters. So that's a good sign. Right? That's exactly what we're looking for when we want to classify. We want to kind of have kind of clear distinctions between the different data sets. More difficult it seems to be to differentiate between the versicolor and the Virginica. There's a clear overlap here, and so we can't make a simple rule like petal width smaller than 1 centimeter to differentiate the two. So you might want to draw a line between here, but then you see that you make some mistakes. So that's not sufficient in that case.
You can say that you have a gray area, but if it is above the gray, then it's definitely Virginia,
Yeah.
and if it is below,
Yeah.
and then when you have this in between, then you need to use other features to distinguish them.
Yeah, I mean you of course, and of course you can now try with the different dimensions, and you get different images. But essentially, kind of the main message that we get out of here is our first feeling for the data is that the blue dots are always fairly clustered away from the gray and the red ones. So what we're hoping is that we should be able to classify that fairly robustly. But it's not clear if we can separate these red and the gray ones robustly. Right? So maybe we have to be more careful there. Okay, so now we've got our data. Now the next step is to train our model. Our setup is that we have 150 observations, we have 4 features, we have the labels for these 150 observations, and we want to use a classification algorithm. And now we need to talk about which algorithm do we want to use. And the simplest classification algorithm that we have is called the k-nearest neighbor algorithm. And the idea is so simple that I can explain it in a minute. So what we have is, what you get is, you get a new iris feature. So someone has collected a new iris flower and has done the 4 measurements, and you're supposed to now tell, or the algorithm is supposed to predict which class it is. The way it does is, well, it picks, k is a parameter that you can choose. So you pick a value for k, so for instance 1, 2, or 3, or whatever. And then what you do is you look for the k nearest neighbors, right? So we have a new point in our 4-dimensional space, which represents this new sample. And now we're looking for the k nearest neighbors in our sample space. And then we return the most popular amongst these. So to give you a specific example, if you just set k equal to 1, we have the 1 nearest neighbor algorithm. We get a new data point in. We find the closest neighbor of the data point, where we know from our training data where we know the label, and then we return the value of that label and use that as prediction. Yeah?
Is that done for each dimension individually or in a single space?
It's done in a single space. So, of course, in 4 dimensions, it's a bit difficult to visualize. I show it in 2 dimensions now, and I hope it becomes very clear. So imagine we have this. Imagine this is our data set. So we have 3 different classes: red, green, and blue, and there you can see they're sprinkled all along. And so now, if you apply the one nearest neighbor classification algorithm, this is the image. This is the outcome. And so essentially, what you need, the way you need to read this is that imagine you want to make a prediction for that specific point here. So these are x values. We have 2 features. We have an x value feature and a y value feature. Maybe just the petal width and the petal length, for instance. And so now I'm making a new measurement point, and that measurement is for that specific petal x and y value of the feature. And so the one nearest neighbor algorithm now looks at what is the nearest point that I have where I know the label. And in that case, it would be that point here, right? And because it's blue, and therefore I also return blue for the prediction of that point. Now if I move to a different point, right, so if here it's all blue, but then at some point here on the edge, I'm closer to that red point, so I'm going to return red as a prediction, and so on and so forth. So this is the one nearest neighbor algorithm. You just look for the closest nearest neighbor and return that class value. And then, of course, if you have the k nearest neighbor algorithm, what you simply do is you take that point, you look at the 5 nearest neighbors in that specific case, and you check what is the majority of the colors that you have. Right? Maybe there are 3 red ones and 2 blue ones, and then you return red as a outcome. And of course, sometimes you might end up with a draw, and this represents here these white arrows. So here you probably have 2, if you're at this specific point here, you might have 2 blue ones, 2 red ones, and 1 green one. And then you can't decide, or it could be red or green. And so then it's just marked as red. So, I mean, that's up to you. If you need to have one, sometimes it's useful to be able to have probabilities of outcomes. So not just have one outcome, but look at all the various different options that you might have. But in that case, you simply can't make, if you need to have one specific answer, then you can just, I guess, make a random choice between red and blue. Okay, I think we should almost have a break. So let's start again at 1:15.